Welcome to today's session. In this video, we'll explore problem number 63, Unique Paths 2. This is a fascinating problem that challenges us to navigate through a grid with obstacles, finding the total number of unique paths from the top left corner to the bottom right corner. We'll break it down step by step, discuss different approaches, and analyze their complexities. Let's get started. In this problem, we are working with a grid represented as an mxn integer array called grid. Each cell in the grid can either be a 0 or a 1. A 0 denotes an empty cell, which the robot can move through, while a 1 represents an obstacle that blocks the robot's path. The robot starts at the top left corner of the grid, which is the cell 0, 0, and it aims to reach the bottom right corner at m1, n1. The robot can only move down or right at any point in time. The task is to determine the total number of unique paths that the robot can take to reach its destination without passing through any obstacles. The output should be an integer representing this count. The input will be the grid, while the output will be the calculated number of valid paths. Let's look at an example to understand this better. Suppose the input grid is a 3x3 matrix 0, 0, 0, 0, 1, 0, 0, 0, 0. In this case, the output is 2, because there are 2 unique paths the robot can take to reach the bottom right corner. The first path involves moving right twice, then down twice. The second path involves moving down twice, then right twice. Notice that the obstacle located at 1, 1 blocks any path that tries to pass through that cell, so those paths are invalid. This highlights how obstacles in the grid can restrict the robot's movement and reduce the number of valid paths. In another example, consider the grid 0, 1, 0, 0. Here, the output is 1. There is only one valid path for the robot, moving down first and then moving right. The obstacle at 0, 1 blocks any path that would involve moving right from the starting position. Finally, in a third example, take the grid 1, 0. In this case, the output is 0 because the starting cell 0, 0 itself is an obstacle. Since the robot cannot even begin its journey, there are no valid paths to the destination. Now let's consider the constraints and edge cases for this problem. The grid's dimensions are defined such that m is the number of rows and n is the number of columns, both ranging from 1 to 100. Each cell in the grid can only be 0 or 1. Importantly, the starting and ending cells are guaranteed to be 0, so the robot will always have a valid starting and ending point. Regarding edge cases, if the grid contains no obstacles, the number of paths will be the maximum possible for that grid size, as the robot can freely move down and right. On the other hand, if the robot is surrounded by obstacles and cannot move away from the start, the output will be 0. Single row or single column grids are simpler, as the robot will have exactly one path by moving continuously in one direction. Finally, since the grid can be as large as 100 × 100, the solution must be efficient to handle potential time and memory constraints. To solve the problem of finding unique paths in a grid with obstacles, the brute force approach relies on the intuition of exploring all possible paths from the top left corner to the bottom right corner. Starting at position 0, 0, we recursively try to move either right or down, checking for obstacles or boundaries along the way. If we encounter an obstacle or move out of bounds, that path is considered invalid and contributes 0 to the count. When we successfully reach the destination, we count that as one valid path. However, this approach has a significant drawback. The recursive branching leads to an exponential time complexity, as it explores every possible path without reusing results from overlapping subproblems. For large grids, this method quickly becomes computationally infeasible due to its high time and space demands. An optimized solution to overcome the inefficiency of the brute force method is the dynamic programming approach. The key idea here is to break the problem into smaller subproblems and store the results of these subproblems to avoid redundant calculations. In a grid, the number of unique paths to any cell depends only on the number of paths to its top and left neighbors, assuming the cell itself is not blocked. For implementation, we create a 2D table where each entry represents the number of unique paths to a specific cell. We initialize the starting cell to 1 if it's not blocked, and calculate the value for each subsequent cell based on its neighbors. If a cell is blocked, we set its value to 0, effectively removing it from contributing to any path. This method has a time complexity of O(m*n) because we compute each cell exactly once, and it uses O(m*n) space to store the DP table. To further optimize the dynamic programming solution, we can reduce the space complexity by using a single 1D array instead of a full 2D table. The observation here is that each cell's value depends only on the current row and the row immediately above it. We initialize a 1D array to represent the first row and update it as we iterate through the grid, row by row. For each cell, if it's not blocked, we update its value based on the current and previous entries in the array. If the cell is blocked, we set its value to 0, ensuring it doesn't contribute to any paths. At the end of the process, the last entry in the array represents the total number of unique paths. This approach maintains the same O(m*n) time complexity as the standard DP method but reduces the space complexity to O(n), making it particularly effective for large grids. The space-optimized dynamic programming approach is the ideal solution for this problem because it strikes the perfect balance between time and space efficiency. While the brute force method is impractical due to its exponential time complexity, and the standard DP approach, though effective, uses more memory, the space-optimized version is both scalable and resource-efficient. By iterating over the grid row by row and using a single 1D array to store intermediate results, we eliminate the need for a full 2D table. This not only reduces memory usage but also simplifies the implementation. Overall, this strategy ensures the algorithm remains fast and memory conscious, making it suitable for handling large grids without sacrificing clarity or performance. The problem involves finding the total number of unique paths in an MXN grid, where some cells may contain obstacles. You are allowed to move either down or right at any step, starting from the top left corner and reaching the bottom right corner. To tackle this, we first consider a brute force approach. Here, we design a recursive function, countPaths, ij, to generate all possible paths from a given cell, ij. If the current cell is out of bounds or contains an obstacle, we consider the path invalid and return 0. If the destination, m1, n1, is reached, we return 1 to indicate a valid path. Otherwise, we recursively calculate the sum of paths by moving right and down from the current cell. While this approach is straightforward, it is highly inefficient due to its exponential time complexity, O(2)m plus n, as each cell leads to 2 recursive calls. To improve efficiency, we turn to dynamic programming. By defining a 2D table DP, where DP, ij, represents the number of unique paths to reach cell, ij, we can eliminate redundant calculations. To implement the dynamic programming solution, we start by addressing the base cases. If any cell, ij, contains an obstacle, we set DP, ij, equals 0 because no path can pass through it. The starting cell, 0, 0, is initialized as DP, 0, 0, equals 1, provided it is not an obstacle. Next, we fill the DP table by iterating through the grid row by row and column by column. For each cell, ij, that is not an obstacle, we calculate its value by summing the paths from the cell above it, DP, I1, j, and the cell to its left, DP, I, j1, if they exist. Mathematically, this is represented as DP, I, j, equals DP, I1, j, plus DP, I, j1. By the time we complete the table, the value at DP, m1, n1, will contain the total number of unique paths from the start to the destination. This approach is highly efficient, with a time complexity of O(m*n), since each cell is processed once. The space complexity is also O(m*n) for the DP table, but it can be optimized to O(n) by using a single row to store intermediate results. The recursive approach, while conceptually simple, suffers from significant limitations. It repeatedly solves the same subproblems, leading to overlapping computations and inefficiency. This makes it unsuitable for larger grids. In contrast, dynamic programming resolves this issue by storing intermediate results in a table, allowing us to reuse them instead of recalculating. This drastically improves performance. One important aspect of the DP approach is how it handles obstacles. By setting DP, ij, equals 0 for cells with obstacles, we ensure that no path can pass through those cells. This effectively prunes invalid paths from consideration. Additionally, we can optimize space usage by recognizing that each state in the DP table depends only on the current row and the previous row. Leveraging this insight, we reduce the space complexity to O(n) by using a rolling array to store only the necessary values. For this problem, the key data structures are the input grid, which represents obstacles and dimensions, and the DP table, which tracks the unique paths to each cell. Together, they enable efficient computation of the result. In the given example, the 3x3 grid includes one obstacle in the middle of the second row. The task is to compute the total number of unique paths from the top left corner to the bottom right corner. The output is 2, representing the two valid paths, one where we move right twice and then down twice, and another where we move down twice and then right twice. The obstacle blocks all other potential routes. To construct the DP table, we initialize the first row and column based on the assumption that paths continue unless blocked by an obstacle. For this grid, the initialization results in the first row being 1, 1, 1, and the first column being 1, 1, 1, with adjustments made for obstacles. As we fill the table, the obstacle at 1, 1 sets DP 1, 1 equals 0, blocking paths through that cell. The final table is constructed as 1, 1, 1, 1, 0, 1, 1, 1, 2. The value at DP 2, 2, which is 2, represents the total number of valid paths. This illustrates how the DP table efficiently calculates paths while accommodating obstacles. Here, we begin by defining a class called solution and implementing the method unique paths with obstacles. The first step inside the function is to determine the dimensions of the obstacle grid, which we store in the variables m and n. These represent the number of rows and columns, respectively. Next, we handle an edge case. If the starting position at the top left corner or the destination at the bottom right corner is blocked by an obstacle, we immediately return 0, as no path is possible in such a scenario. After addressing this edge case, we initialize a dynamic programming grid, or DP grid, with the same dimensions as the obstacle grid. Each cell in this DP grid will eventually represent the number of unique paths to that cell. We set the starting position, DP 0, 0, to 1 since there is exactly one way to start at the top left corner. To prepare the DP grid, we first populate the first row. If a cell in the first row isn't blocked by an obstacle, we inherit the value from the cell to its left. Similarly, we populate the first column by checking for obstacles. If a cell isn't blocked, we inherit the value from the cell above it. This ensures that the initial row and column are correctly set up before we move on to filling the rest of the grid. Now, we focus on filling the rest of the DP grid, which represents the core of the solution. For each cell, starting from the second row and second column, we first check if the cell is blocked by an obstacle. If it is, the number of unique paths to that cell remains 0, as no path can pass through it. However, if the cell is not blocked, the number of unique paths to that cell is the sum of the paths from the cell directly above it and the cell directly to the left of it. This is because any path to the current cell must either come from the top or the left. After iterating through all the rows and columns, the DP grid is fully populated with the number of unique paths to each cell. Finally, we return the value at DP M1, N1, which represents the total number of unique paths to the bottom right corner of the grid. This gives us our desired result, efficiently calculated using dynamic programming. Here, we begin with the Java implementation of the solution. First, we define a method unique paths with obstacles that takes a 2D integer array obstacle grid as input. This grid represents the maze where some cells may be blocked. We start by determining the dimensions of the grid, m for the number of rows and n for the number of columns. Next, we handle an important edge case. If the starting point at the top left corner or the destination at the bottom right corner is blocked, we immediately return 0 since no paths are possible in such scenarios. We then initialize a DP array with the same dimensions as the grid. This dynamic programming array will store the number of unique paths to each cell. The starting point, DP 0, 0, is initialized to 1 because there is exactly one way to be at the starting point. After that, we proceed to fill the first row. If a cell in the first row is not blocked, it inherits its value from the cell to its left because the only way to reach it is from the left. Similarly, for the first column, if a cell is not blocked, its value is determined by the cell directly above it, since the only way to reach it is from above. Now, after handling the first row and column, we move on to filling the rest of the DP grid. Using nested loops, we iterate through each cell starting from DP 1, 1. For each cell, if it is not blocked, i.e., its corresponding position in obstacle grid is 0, its value is calculated as the sum of the paths coming from the cell above it and the cell to its left. This ensures that we account for all possible ways to reach the current cell, whether from above or from the left. Finally, after populating the entire DP grid, the bottom right corner of the grid, DP M1 is in 1, holds the total number of unique paths that can be taken to reach the destination while avoiding obstacles. We simply return this value as the result of our method. Here, we start with a simple example of a 3x3 grid that has no obstacles. The first step is to initialize the dimensions of the grid, which are m equals 3 and n equals 3. Next, we create a DP table of the same size, filled with zeros. This table will help us calculate the number of unique paths to each cell. The starting cell, DP 0, 0, is set to 1 because there's only one way to start the journey. After this, we fill the first row. Since there are no obstacles, each cell in the first row gets its value from the cell directly to its left. Similarly, we fill the first column by copying values from the cell directly above. At this stage, the DP table reflects that all cells in the first row and column have exactly one way to reach them. Now, we calculate the number of paths for the rest of the grid. For each cell, the value in DP I, j, is the sum of the paths coming from the cell above it, DP I1, j, and the cell to its left, DP I, j1. For instance, at DP 1, 1, the value is 2 because there's one path coming from the top and one from the left. Similarly, at DP 1, 2, the value becomes 3, as it's the sum of the values from above and left. We repeat this process for all remaining cells, arriving at a final DP table where the bottom right cell, DP 2, 2, contains the total number of unique paths, which is 6. This means there are 6 distinct ways to traverse the grid from the top left to the bottom right corner. In this example, we introduce obstacles. Here, we have a 3x3 grid where there is an obstacle at cell 1, 1. We initialize the DP table as before, setting DP 0, 0 to 1. The first row is filled by propagating the value from the left, provided there's no obstacle. Similarly, the first column is filled by propagating the value from the top, ensuring no obstacle blocks the way. After these steps, the first row and column are completed, and paths are blocked appropriately by the obstacle at 1, 1. This setup prepares us to calculate the rest of the grid while respecting the obstacle. To handle the rest of the grid, we calculate paths for each cell, skipping any cells where obstacles are present. For example, at DP 1, 1, we set the value to 0 because it's an obstacle. For other cells, the value is computed as the sum of the paths from the top and left cells, but only if those cells are accessible. At DP 1, 2, the value is 1 since the obstacle at 1, 1 prevents any contribution from the left. Similarly, at DP 2, 1, the value is 1 because no paths come from above due to the obstacle. Finally, at DP 2, 2, the value is 2, which represents the total number of unique paths to the bottom right corner. The obstacle has effectively reduced the possible paths, leaving us with an output of 2. In the last example, we encounter a case where the start or end point is blocked. Here, the starting cell, obstacle grid 0, 0, is occupied by an obstacle. Since it's impossible to begin the journey, we terminate early and return 0 as the result. This demonstrates how obstacles at critical positions can completely eliminate the possibility of any unique path in the grid. To analyze the time complexity of this algorithm, we begin by considering the operations involved. First, the initialization of the DP grid takes m*n time since we're creating a 2D list with m rows and n columns, and each cell is initialized to 0. Next, we handle the first row, iterating through its n cells to update values based on the presence of obstacles. This step requires n time. Similarly, the first column, with m cells, is processed in m time. The most significant contribution comes from filling the rest of the DP grid. Here, for each cell, I, j, we compute the number of unique paths by adding the values from the cell directly above and the cell to the left. This computation is performed for all cells from the second row and second column onward, which involves m1, n1 operations. When simplified, this is also m*n. Combining all these steps, the overall time complexity is O, m*n. Now, since all the operations, including initialization, the first row and column updates, and the main grid filling, are dominated by the O, m*n term, the total time complexity is confirmed to be O, m*n. Shifting our focus to space complexity, the algorithm also requires O, m*n, space due to the DP grid, which is used to store the number of unique paths for each cell. This grid has dimensions mxn, and its storage dominates the space usage. The input grid, obstacle grid, is provided and doesn't add to the algorithm's space complexity. Additionally, auxiliary variables like m, n, and indices such as I and j only require constant space, O1. Therefore, the total space complexity is determined by the DP grid and remains O, m*n. Let's compare this dynamic programming approach with a brute force solution. A brute force method would involve exploring all possible paths from the top left to the bottom right cell recursively, while avoiding obstacles. At each cell, there are two choices: move right or move down. This results in an exponential time complexity of O, 2m+n, as the recursion could generate up to 2m+n paths in the worst case. The space usage for the recursion stack would be O, m+n. In contrast, the dynamic programming approach eliminates redundant computations by storing intermediate results in the DP grid. This optimization reduces the time complexity to O, m*n, and the space complexity to O, m*n, making it significantly more efficient than the brute force solution. Let's consider the best, average, and worst cases for this algorithm. In the best case scenario, where there are no obstacles in the grid, the algorithm still performs O, m*n, operations to calculate the unique paths. For the average case, where the grid contains a moderate number of obstacles, the algorithm processes all cells regardless, resulting in the same O, m*n time. Even in the worst case, where every cell except the start and end points is an obstacle, the algorithm still scans the entire grid, leading to O, m*n time. In this worst case scenario, most DP values will simply remain 0. From a mathematical perspective, the algorithm iterates through all m*n cells exactly once, and there are no nested loops beyond these iterations. Consequently, the time complexity is O, m*n. Similarly, the space complexity is determined by the size of the DP grid, which occupies O, m*n space. When solving problems like unique paths 2, there are a few common mistakes to watch out for. First, not handling edge cases explicitly can lead to errors, especially for grids with only a single row or column. For example, a 1xn grid only has one path, yet overlooking this can produce incorrect results. The solution here is to always test these edge scenarios and account for them in your implementation. Another mistake is misidentifying overlapping subproblems in dynamic programming. If you fail to recognize that paths to a cell can be reused, you'll end up recalculating results unnecessarily. To fix this, use memoization or a bottom-up DP table to store intermediate results. Lastly, errors in recursive solutions often come from incorrect base cases. Forgetting to stop recursion for out-of-bound indices can cause infinite recursion or runtime errors. To avoid this, define base cases clearly, such as returning 0 for invalid cells and ensuring the bottom right corner is handled properly. Now, another common pitfall is relying on inefficient brute force solutions. For instance, generating all possible paths recursively without pruning leads to an exponential time complexity of O, 2m+n, which is far too slow for larger grids. The fix is to use dynamic programming to reduce this complexity to O, m*n, making the solution much more efficient. Hard-coding grid dimensions is another issue to avoid. If you use static array sizes or write code for specific grid dimensions, your solution won't adapt to different inputs. Instead, always ensure your solution dynamically handles any grid size by deriving dimensions directly from the input. To do well in interviews, it's essential to focus on dynamic programming, as optimized solutions using DP are typically expected. Practice explaining how recursion transitions to DP and how overlapping subproblems are solved, emphasizing how memoization reduces redundant work. Clarifying edge cases is also crucial. Always ask about constraints like minimum grid sizes or whether obstacles are part of the grid. Interviewers often appreciate discussions around trade-offs, such as the space difference between recursion with memoization, which uses O(m*n) space, and iterative DP with rolling arrays, which reduces space to O(n). Finally, if the problem involves counting paths, make sure to clarify details about diagonal movements, obstacles, or weighted paths, as these can change the approach. For related practice, consider problems like LeetCode 62, which focuses on a simple grid without obstacles, or LeetCode 64, which shifts the focus to minimizing path sum instead of counting paths. For alternative approaches, recursive brute force is the most straightforward to implement but has exponential time complexity, making it unsuitable for large grids. It's best used for understanding the problem conceptually or demonstrating brute force on very small grids. Memoized recursion improves efficiency by reducing redundant calculations, but it still carries the risk of stack overflow due to recursion depth in larger grids. Iterative dynamic programming is the most efficient and preferred in interviews, offering optimal time complexity of O(m*n) and space complexity as low as O(n) with rolling arrays. Finally, for variations where the grid is simple and contains no obstacles, combinatorics can be an elegant solution with O(1) time complexity. This approach works by counting combinations of moves, such as m down and n right, but it's only applicable in specific scenarios where obstacles or other constraints are absent. Great work! In this session, we tackled problem number 63, Unique Paths 2, and reviewed multiple approaches, including brute force and dynamic programming. We highlighted the importance of analyzing edge cases and optimizing solutions for efficiency. Remember, consistent practice is key to mastering dynamic programming problems. Thank you for joining. Don't forget to like, share, and subscribe. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!